Hello. We are just passing into noon right now, so I am going to go ahead and start by welcoming you all to Introduction to Finishes and Alloy Selection, brought to you by AIA provider, the International Molybdenum Association, IMOA, and co-sponsored by the Nickel Institute. Both are trade associations who sponsor research and provide independent technical information related to molybdenum and nickel-containing materials. If you'd like to learn more, I will place links to both associations in the chat. Couple of housekeeping items. Please save your questions for a Q&A session at the end of the webinar. We'll reserve about 10 minutes for that. Also, if you are seeking AIA CES credit or a certificate of completion, please note that you must stay on for at least 45 minutes, preferably, of course, the entire webinar, but we cannot give you a certificate if you are not on for at least 45 minutes, so please bear that in mind. Okay, now let's meet our speaker, Catherine Houska. She is an internationally renowned expert in architectural and structural metals who actively participates in multiple standards committees, including AISC 370 and 313, as well as chairs the ASTM E60-80 General Sustainability Committee. She has authored over 200 publications, including contributions to AISC's Design Guide 27. So I am very pleased to welcome Catherine, who will now lead us into our presentation. Thank you all for joining us today, and without further ado, here is Catherine.
Hello, everyone. I'm so glad that you could join us today. This presentation will be kind of an introductory overview of the key things that you need to know about finishes and alloy specification. The materials are copyrighted, and you will receive credit if you stay on for at least 45 minutes. Everything I say today is a suggestion for your consideration, not a recommendation. I'm sure you've all seen the learning objectives. We're going to talk about common stainless steel alloys and families and finishes. There are other presentations that delve more deeply into these, so we do hope that you watch for future webinars that we're giving in general, or perhaps you could organize them for your firms. And we will delve into some of these basics. First of all, I sometimes encounter the misconception that stainless steel is not iron-based. It is. It contains iron and at least 10.5% chromium and is low carbon. That's the ASTM definition for stainless steel. That chromium allows it to form a protective passive film. The chromium, molybdenum, and nitrogen levels are what most affects corrosion performance. With carbon steel, which is higher in carbon and has less chromium, you will form gross corrosion on the surface. The entire surface will corrode. With stainless steel, you formed a passive film that improves the corrosion resistance. So with that, we get pitting corrosion rather than the uniform rapid thickness loss that occurs with carbon steel. And these images show that. I did clean the stainless steel sample to get rid of the light corrosion staining so that the small pits could be seen on the surface. There are a number of fundamentals that are important to understand. First of all, when someone from the stainless steel industry uses the word grade, they typically mean chemical composition. I'm pointing this out because usually for aesthetic applications for stainless steel, the word grade for other materials means either strength level or quality level, and that's not the case with stainless steel. Additionally, it is critical to use the UNS number. Those are shown in the ASTM specifications. In your alloy specification, it points the supplier to a very specific alloy and avoids confusion. Simply using a common name, much less saying stainless steel, is not adequate in terms of specification. Additionally, for most product forms, you will use 2 ASTM standards for that specification. I'll get into that a bit later. Stainless steel gauges are not defined in any standard. Individual suppliers may have their own internal definitions, but that is not something that is legally binding and consistent. So it is critical to specify the thickness, whether inches or millimeters, the minimum that's required, the maximum or acceptable range. Don't use gauge number. It's misleading, and it's critical to understand that the typical meaning of a gauge thickness with stainless steel is a different thickness than for carbon steel or for aluminum. So you cannot assume that it will all be the same. As I mentioned, saying stainless steel on your drawings and project specifications is not enough. Specify the alloy using the UNS number. I'm reiterating that because it's very important, and I far too often simply see stainless steel called out. Or just a common name like 304, but not a UNS number, something that points to the very specific alloy that is required and is clearly shown as the first line in the chemistry tables in the ASTM specifications. That brings me to the next point. Read the ASTM specifications you're ordering to. I too often see simply the specifications called out. If you read the specifications, there is a section that has the ordering requirements. It lists the specific things that the specifier has to request, the decisions that you need to make. If you have not made those, then you have to assume that the fabricator or seller will sell you the least expensive option, which may not be what you really need for your project. For finishes, the descriptions are deliberately vague, not just in ASTM, but also the EN standards and any of the finish standards around the world for stainless steel. So it is critical to quantify what is needed. If you need finish matching, or a certain smoothness. For example, if a high level of cleanliness is required, for example, for pharmaceutical or medical or other applications, then you need to specify a maximum surface roughness. For appearance matching, surface roughness, gloss, and color, with color being a measurement, that would be needed for some of the colored stainless steels. But if you haven't identified that those specific requirements, then you could have variation. It's also important to have a control sample so that you can visually see what was agreed between all parties, because you could have the same surface roughness and gloss and have a long polish line versus a short polish line or something else that will cause a change in appearance. One of the things that we are going to be providing links to is our downloadable library of stainless steel publications. One of the items in that list, in that library, is a list of ASTM specifications as well as some other specifications. And by product form, it tells you which ones you need to use as you specify. For plate, sheet, and strip, the two primary specifications that you will be using are ASTM A240 for chemistry and mechanical properties. There are some optional tests in that specification should you need them. A480 covers everything else: the finishes, the dimensional tolerances, the packaging, anything else related to the purchase of that material. And within 480, you should be making some decisions and about what you need. And we'll talk about a few of those. I regularly see ASTM A666 called out for architectural or aesthetic applications. It is the wrong specification to use. It's intended for cold work structural applications. So don't use that for curtain wall or roofing or anything that's not structural. If your specifications still list A167, then they are seriously out of date. It has not been the right specification for standard sheet, strip, and plate for over 30 years. And I think it was about 15 years ago that we actually withdrew the specification in ASTM to try to stop people from using it when they should have been using 240. So take a look at your in-house specifications and see if they are correct or not. For an aesthetic application or any application where you need flat panels, then one of the options within ASTM A480 is tension leveled quality of flatness. That could be achieved through stretcher or tension leveling. So if wavy panels are not acceptable, then you need to require that. And as I said, it is an option. So, and I should point out as well that if you have not, required a very flat stainless steel panel, then if it is polished in between when it's wavy, you'll get inconsistencies, and really with any finish application there'll be inconsistencies simply because the panel wasn't flat to begin with. And yes, panel fabricators can use their process to flatten the panels, and there will be some movement after they're cut. But if they're not flat when the finish is applied, that's the starting point for an inconsistency issue. The most common stainless steels used are 304 and 316. I've listed the L versions as well. In the US and in Europe, generally everything is dual certified as 304, 304L. That's not true throughout the world. And some parts of the world, they actually charge a premium for low carbon. Low carbon L is needed when you are welding anything that's 1/8 of an inch thick or thicker to prevent sensitization. For other applications, if you're simply cold forming, then you don't need that low carbon. Type 304 is fine for climate controlled interior applications, rural and suburban areas. But if there's going to be pollution, even if it's fairly low levels or salt exposure, it may not be the right choice, especially if it's aesthetic and you want it to be stain free. If it is going to be used, you'll have to have a very smooth finish and clean it regularly to avoid a staining issue. And for some finishes, any staining could destroy them. And I'll point that out as we get into that section of the presentation. It's better to be more conservative. Type 316 is fine if you have low to moderate industrial pollution, moderate to high urban pollution. For lower levels of coastal and de-icing salt exposure, if you get into high levels, you should expect staining. Unless you're, if you're using a very smooth finish and someone is cleaning very regularly, then you could avoid that. But that often doesn't happen. Now, those are only 2 stainless steels, and there are many more that are used in architectural and structural applications. This graphic shows you different stainless steels as part of their chemistry and the PREN number. The PREN number is the pinning resistance equivalent number. You can calculate the relative corrosion resistance of stainless steels using the chromium, molybdenum, and nitrogen content. I'm showing an equation at the bottom that's representative of that. The lower the number, the lower the corrosion resistance. So the precipitation hardening stainless steel, 17.4 pH, only has a score of 15. 304 is at 18. The lean duplexes in type 316 are around 25. 2205 duplex is another 10 points higher at 35. And then we have stainless steels that are up in the 40s. The stainless steels that are up in the 40s could be immersed in sea and brackish water or an industrial stream and not corrode, depending on the choice of alloy. 316 would definitely corrode if you put it in brackish or seawater. So the level of corrosion resistance is important if you need long-term performance, especially if you want stain-free performance. This is another way of looking at it with a few more alloys. I did want to point out this is color-coded based on alloy family. The ferritics in blue, austenitic in orange, duplexes in green. As you can see, at every level of pitting resistance, there are multiple alloys in different alloy families. Your starting point for assessing the environment and determining which stainless steel would be most appropriate are these two. Which stainless steel should be specified for exterior applications from the International Molybdenum Association is a scoring system that walks you through the factors that are important in selecting the right stainless steel and finish combination for your application. It assumes that you will not want corrosion. The Nickel Institute brochure, Guidelines for Corrosion Prevention, it goes into more depth on some of these same topics, as well as talking about some of the different types of corrosion, like galvanic corrosion, in terms that are intended for the non-metallurgist. Additionally, we have both papers and articles that are specific to topics like coastal and de-icing salt, and immersion in salt in different waters, swimming pools, the different types of environments that you might encounter. And those are all on the library that you can download. Since we're talking, about, I'm assuming that most are focused on architecture and atmospheric corrosion. So these are the considerations that are necessary as you're selecting a stainless steel. Is there pollution? What type? Look at the localized emissions. Is there particulate accumulating on the surface? Will there be coastal or de-icing salt exposure? Is there regular heavy rain? Or do you have long periods without rain, but high levels of humidity? Will there be any cleaning? Does the design add potential corrosion issues like crevices or a rougher finish? And then you should consider handling issues that might also have an influence. So this is data from the U.S. National Atmospheric Deposition Program. Anyone can log on and look at these maps. They're done annually. There's usually a couple-year lag time before each is released. You can look at the acid rain for an area or different types of pollutants. In this case, I was specifically looking at total salt or chloride deposition. You can see the influence of the salt lakes, but you can also see that salt is not just right on the coast. It can be quite far inland. And that dark reddish color is an indication of areas with significant salt deposition from either rain or dry salt particles. So 60% of the population is in an area with at least some coastal salt. The American Wood Council recently changed their specifications to require type 316 fasteners and other fixings for decks in any area that falls into these dark red areas. And so it is applicable for a range of applications, and those are generally areas where you should be thinking type 316 or higher. De-icing salt is another big issue. In the US, 70% of the population is in an area where there's at least some de-icing. And I should, going back to the prior slide, point out that 60% of the world's population is also in a coastal area. So this is not just US specific. For de-icing, any part of the world where snow and ice tends to be an issue is generally de-iced. This is US data. This particular study documented that dry salt particles travel at least 1.2 miles downwind from roads, from larger roads, and were found as high as the 59th story of a building in downtown Chicago. I've documented de-icing salt as far as 2 miles from a rural highway, and it was affecting the top of a building. So there was no question as to where that salt was coming from. The bottom of the building was fine, and it was downwind of a highway 2 miles away. So it should be considered as you were designing. And we've made a lot of changes in what we're using to de-ice. It used to be sodium chloride, rock salts. And when we used sodium chloride, until you reached a temperature of 50 degrees, you had, and 76% humidity, it couldn't pull moisture out of the air and create a salt slurry on the surface. For calcium and magnesium chloride, which are increasingly being used as both as pre-treatments and in colder regions when the temperatures are going to go lower, all you have to do is be above freezing and at least 45% humidity, so very little moisture, relatively speaking, for it to start pulling moisture out of the air and creating a salt slurry on surfaces. And these are calcium magnesium chloride are highly aggressive chlorides for deterioration of any material. So often de-icing salt applications are more corrosive than many that are in coastal areas, but you can, of course, have both. If you are designing a project that's going to be, one of these new developments that's going to be floating on water, well, you really should consider whether the materials can withstand salt water. 316 most definitely is not a seawater grade stainless steel. The stainless steels or any of the metals in general that are necessary to withstand salt water are far more corrosion resistant. Also, please consider whether or not flooding is likely. I'm showing a picture of New York when the subway tunnels, some of them were immersed for quite long periods of time in brackish or salt water, which caused a lot of corrosion issues. So please consider in your designs the correct stainless steel, and it won't be 316 or 304. 2205 is fine for shorter term applications, maybe 20 years or less. You probably have to go to an even higher level of stainless steel for immersed applications otherwise, but that can vary, and it's important to speak to an expert in that specific type of corrosion. There is a great deal of data that's been collected around the world documenting the relative corrosion resistance of different stainless steels. This happens to be data from Dubai. Parts of the Middle East are extremely corrosive with high levels of salt deposition, lots of fine particulate in the air, and while the average humidity is low at night, there is enough so that water accumulates on surfaces. And that combination of very little rain to wash away the accumulations, but enough to certainly dampen them at night, creates a highly corrosive situation. In this study, a variety of metals were included. I mean, this is a location where 316 would exhibit corrosion staining pretty quickly. So, but 2205 duplex did very well. Unfortunately, galvanized steel and the zinc that protect it corrode very quickly, as do aluminum and copper in this type of environment. But there's data, it's all a matter of picking the right metal for the location. This is data from South Africa. Again, comparing multiple metals. They had also included aluminum and copper in this comparison, although it's not in the specific table. If you look, some of these locations are fairly rural, while others like Durban Bay and Walvis, Durban Bluff and Walvis Bay are severe marine environments. And you can see the dramatic differences in corrosion rate associated with the different aspects of the service environment. Salt levels and moisture exposure, humidity range, all play a big role. You don't necessarily have to have a corrosion test site near where you are, but if there are similar sites with similar environmental characteristics, you can use that to predict likely performance. I live in Pittsburgh, and these were all panels on buildings in downtown Pittsburgh that had not been cleaned in about 3 years. We do use de-icing salt, and there is some pollution. All of these have a number 4 finish, so a fairly smooth number 4 finish. It was pretty comparable. You can see the different levels of corrosion after 3 years without cleaning. The 430 has pretty significant corrosion, which would require refinishing truly to restore it. The 304, wiping that with a damp cloth pretty much takes care of it. although you'd want to do a bit more than that to make sure the salts are really gone. With the 316, there's some bird droppings evident, and you could see some salt on the surface, but it looks fine in this particular application. Surface roughness can make a big difference. The rougher the surface, the more pollutants and salt and particulate can accumulate on the surface. It will also, a rougher surface will also retain moisture longer. So all of that increases the rate of corrosion. And for any material with a rougher surface, you will accumulate more of what's corrosive, and so the risk is higher. With stainless steel, generally, if you have a surface roughness of 0.5 microns or 20 microinches or less, the corrosion rate is substantially lower. If you're above that line, then we see a rapid increase in corrosion rate. And I've listed some finishes that can fall in one category or the other. Number 4 is on both sides because sometimes it's rough and sometimes it's quite smooth. In a couple of our publications, we have surface roughness ranges. I did a survey to find out what the typical surface roughness ranges are for different finishes. Now, this is in light gauges, light, thinner sheet and strip, not for heavier plate. And you can see the variation in number 4 from quite smooth up to quite rough. And it's all a matter of specification. But so that is part of what you have to consider. I'm not going to delve into this, but if you have crevices in your design and they are not sealed, then you can have crevice corrosion. This is not galvanic, this is strictly crevice. And you sometimes on projects, all of the corrosion is right around those mechanical fasteners that haven't been sealed. But that can lead to problems that might not otherwise occur. Galvanic corrosion also has to be considered. It will not be the stainless steel that corrodes. It will be the aluminum or carbon steel that you connected it to. And surface area ratio plays a role in this too. If you have a large surface area of stainless steel and you've chosen to support it with aluminum or carbon steel, and there's no separation, then that aluminum or carbon steel will corrode at a highly accelerated rate, and both are already less corrosion resistant than stainless steel. So as we are specifying stainless steel finishes, please use a legally recognized finish standard, whether it's an ASTM standard or EN or JIS, wherever in the world you happen to be working. Do not treat the industry association guidelines like standards. I so often see them called out in project specifications. They are not legally binding. They are general descriptions. So you have to create a tighter standard to get what you want. And that means agreeing on a visual standard, agreeing on a surface roughness range that you find is acceptable after you've looked at samples, and a gloss or reflectivity range. If you can, describe the grain length. I mean, there's a difference in appearance between a number 4 finish and a hairline. If there's any pattern, directionality, anything that you can describe that affects the aesthetic appearance that you want to achieve is important to spell out. And of course, have a visual standard. I'm going to be showing a variety of finishes. All can be obtained on the Austenitics, like 304 and 316. And those stainless steels, which have an austenitic microstructure, are strengthened by cold work. Tight bends and welding are pretty easy. They are non-magnetic. It's part of why they are often favored for architectural applications. There are far more limited finish options on the ferritic stainless steels. Those have the most limited finish options. That includes alloys like 430 or 444. They are less formable and welding can be tricky. You really should be done in the shop. They are magnetic. The duplex stainless steels also have more limited finish options, but they're in between the austenitics and ferritics, and their microstructure contains both austenite and ferrite. 2304 and 2205 are two examples. They are higher in strength. They're about double the strength of the common austenitics. You typically get more corrosion resistance for the dollars, and they are magnetic. They're a good choice for structural applications, but I've also seen them used for applications like roofing and curtain wall in more corrosive environments. To obtain a more uniform appearance, it's important to use one coil or consecutive coils from one supplier to mark the rolling direction on the film so that you can make sure that all the panels are installed consecutively in the same direction. Otherwise, you could end up with a checkerboard appearance or one panel upside down among a field of many. That top image are all panels taken from the same panel of stainless steel, but then some were turned 180 degrees. Directionality affects color. The bottom image shows the roof of where the Pittsburgh Penguins used to play. It's an example of what happens when you have multiple suppliers, and there were 4 stainless steel suppliers for that roof. Of course, that was back in the 1960s. It is possible to obtain a high level of uniformity if you have tight specification and work closely with a good supplier, as is shown here. Please consider whether you really need a reflective finish. If you have 2 finishes that are equally flat and one is dull and one is highly reflective, you can get this kind of difference. The mirror-like finish looks wavy when it is the same flatness as the dull. Now, a finish that perhaps sparkles but diffuses light would behave more like the dull finish. I wanted to quickly go through a couple of the common ASTM A40 finishes. 2D, more common. It used to be the standard finish for roofing. Now it's mainly something that you see on plate. It's basically a pickled and blasted finish. A 2B mill finish. This is commonly used for flashings and downspouts and industrial roofing where you're not worried about consistency, but it's also the starting point for many finishes. It also varies more in appearance than any of the other finishes, can range from cloudy to almost mirror-like. So it's generally not something that would be acceptable to use as is for any large surface. The bright annealed finish is the result of heat treating in a furnace without oxygen. So there's no mill scale to remove, and you end up with a mirror-like finish. Sometimes this is used buffed in architectural applications and is suitable for ornamental applications, but it's not the same as a highly polished and buffed Super No. 8. A number 4 finish can vary substantially in appearance. It all has short parallel directional lines when applied to sheet or strip. Somewhat repairable, but generally you're going to end up with a hairline finish, which I'll talk about next. Please do not use grit to specify this finish. You could have 2 finishes with the same grit that look very different. Always use the surface roughness, gloss, and other characteristics to specify. The hairline finish was developed by the Japanese. There is no ASTM standard. It has directional, long, fine, parallel lines. Most often it's applied with Scotch-Brite pad, but it's non-metallic abrasive pads that are dragged over the surface. It is more reflective than a number 4, much more repairable. So when you refinish a number 4, it generally becomes a hairline. And a nice smooth surface. So if you're looking for something that is a more of a jewelry-like, consistently fine, repairable finish, this is actually a better choice than number 4. Number 8 is also covered by the ASTM standards. This is stainless steel that has been polished and then buffed for generally around 15 to 20 minutes. You can still see the remnants of the fine polishing lines if you look closely. Be careful about where you use it, to make sure that it's not going to cause reflectivity issues. The super or supreme number 8, 9, 10, 11, 12 is usually a finish that has been polished, abrasively polished, and then buffed for up to 60 minutes. But sometimes people sell a buffed bright annealed finish as one of these. So if it's seems like a very good deal, it might be a buffed bright anneal. The advantage of abrasive polishing is that you're going to get rid of blemishes in the surface that might matter for some aesthetic applications. Low sulfur is important for 2 reasons. First of all, corrosion performance, and second of all, finish. So those sulfides on the surface, if not removed by passivation, can be places where corrosion occurs. Additionally, if you're polishing to a high level, a mirror type finish, if it's a higher sulfur stainless steel, you can see little pits where the sulfides were pulled out, which is undesirable. So for a fine or mirror-like finish, you really want to specify 0.002% sulfur or less. For other finishes, you could go with 0.005% or less. Keep in mind that for bar, tube, and pipe, you may not find low sulfur because the sulfur is added for high-speed welding and machining. The vibration finish, also sometimes sold as angel hair, suede, or called a non-directional polish, is applied by most often by the same method that's used for hairline with non-metallic abrasive pads moving in different directions, but it could also be applied with stainless steel wire brushes. It can vary substantially in appearance, as you can see from these 2 images, short versus long scratch lines, different densities of scratch lines. So it's important to document exactly what you want and describe it in your specifications, as well as having control samples. The distress finish, sometimes called pre-vandalized, is also non-directional, but is made with either a grinding wheel or coarse stainless steel wire brushes. So this is a much rougher finish, and which means it's much more likely to accumulate whatever is corrosive. or to accumulate dirt as a whole. So it can cause more cleaning issues, but it's wonderful for hiding accidental scratch damage in interior applications. The swirl finish is the same exact concept, but in more of a pattern. This is generally applied using, a computer-controlled setup to create a consistent pattern, although it could be done by hand. These last two finishes are quite rough, so you generally would not want to use them outside. Otherwise, you might have a corrosion issue that wouldn't otherwise happen with a smoother finish. Abrasive blasted finishes can vary in appearance based on the blast media that is used. If it is actual abrasive blasting done by hand, you have to take into consideration the thickness of the panel and how well fixtured it is. If it's too thin or not well fixtured, you can cause surface distortion. In many instances, you'd have to blast on both sides to try to even that out. If it's done by hand, the appearance is generally not consistent. It tends to be a finish that's susceptible to fingerprinting. So it is, there are some fallbacks, some potential problems with this, but it is the finish that is on most structural sections. For embossing and coining, there isn't really a relevant ASTM standard. ASTM A947 does cover this product, but for industrial applications, it does include some suggested requirements for the variation in pattern height, but that it's on the verge of being withdrawn, so I wouldn't use it. These finishes are applied by applying stainless steel coil between two rolls. When one is patterned and the other smooth, you get a one-sided coined pattern. Finishes like linen are a popular example of a coined finish. Embossing is when both rolls are patterned and you have a two-sided finish that gives you much more cold work and creates a much more impact resistant finish. Either of these finishes presses a pattern in, so it cold works the stainless steel and increases the scratch and impact resistance of the stainless steel. In this test, the sample with the deepest scratch marks at the top, the highest weight, you can see a little bit of that at the bottom. They did scratch the bottom and the top, but you can see how well it helps to protect the surface from scratching damage. Embossing and coining can also be applied over customized finishes. There are some suppliers that will do custom embossing of different shapes onto surfaces on individual panels. Sometimes it's combined with paint or electrochemical coloring to create different appearances. So there are a number of possible variations. It's important to note that if you like the appearance of abrasive blasting, but you're using a thinner sheet or strip or have a roofing application, the standard finish that has been developed in recent years for dull roofing applications, those that will meet the requirements for airport roofs. There are rolled on finishes that have been developed by numerous suppliers around the world that look like abrasive blasting, but they're on light gauge stainless steel and they're pressed on. It does give you a very uniform appearance. It's a lower cost than abrasive blasting. and has improved corrosion resistance over a blasted surface. Electrochemical or light interference coloring has been around for a long time. It's similar to anodizing aluminum. What happens is as you place the stainless steel in this electrochemical bath for a longer period of time, it thickens that passive film, which then filters out wavelengths of light and gives you an array of different colors. So you can then get a range of colors, as I'm showing here, or if it's gradually pulled out, a deliberate rainbow effect, as has been used in some artwork. It's important to understand that these colors are not going to be absolutely consistent because of how the coloring method is achieved. It varies with the color as to how consistent it can be. And here's an example on the Experience Music project. You can see some of that variation. I did want to point out that this coloring method has been used on both austenitic and duplex stainless steels effectively. For the ferritics, you only get a lighter gray color. If there is any corrosion of electrochemical coloring or any of these more fragile finishes, then you can cause damage that is purely aesthetic, but may no longer be acceptable. So this was an example of type 316 stainless steel that was electrochemically colored, being used by the shoreline, and salt spray got onto the roof. It was enough, even though this staining was very superficial, to cause permanent color change. So it is better to be more conservative if you're using a colored stainless steel to avoid this type of problem. Sputtering or plasma vapor deposition is another coloring method for stainless steel. There is tremendous variability in the quality of this finish, so it's very important to specify it carefully. This is a very thin adherent film, if properly produced, that doesn't fade with UV. Neither of these coloring methods do. And you can get a whole range of different colors. It's often used to obtain copper-like colors without a color change. One recent high-profile example is the vessel at Hudson Yards, which has a red-gold PVD color on type 316 stainless steel. Now, that was very carefully specified. I was involved in that project, but there are other project examples where the quality of the PVD was not particularly good, where there's been delamination fairly quickly. So you want to use a very good supplier. You want to make sure there's a titanium underlayment, and a variety of other things are done if it will be an exterior application. If you're not going through thermal cycling, then it is a bit easier to avoid issues. Woven stainless steel adds a wide variety of textures. It can be wonderful for scratching and impact resistance. Keep in mind, in an exterior application, this is full of crevices, so you need to specify a stainless steel that will not cause a crevice corrosion issue over time. This one of the applications for this finish is for sunscreens, as you can see in the Second Children's Activity Center in Guangzhou. I did want to reiterate that we do have a library of stainless steel information that you can download. Everything's broken down into file folders by topic so that you don't get this huge dump of PDFs without a way of understanding what is included. For technical help, the Nickel Institute has a an inquiry system that's happy to help you with your questions. And with that, I'm happy to entertain any questions that any of you might have.